Okay, so thanks a lot, Florent, and thanks a lot to the organizer for giving the opportunity to speak here. So I'm going to tell you about some works, actually make some kind of short review and talk about more recent work in this field. So the fields of trying to model protein from sequence data. So this is a field which is involving a lot of people. Some of these people are here, for instance, and I will cite some of their works later on. And this is a field which is, let's say, at the crossroads between computational biology, machine learning, statistical physics, and maybe statistics, and a lot of other disciplines. So, so during the talk, I'd like to essentially present the problem we are considering, and the kind of data that people have to tackle this problem, and then talk about the existing methods, and briefly present some current application of these methods. And then I'll try also to go to more theoretical issues at the end of the talk, in particular related to the existing methods, why they work, and what could be maybe improved in these methods, and also extension to other methods coming from machine learning, which have not been tried too much so far in the field. Okay, so so what is the problem? So the problem is essentially try to understand let's say, the mapping between sequence and function structure in proteins. So this is a very old problem that people have asked a long time ago. So what is a protein? So protein, so it's going to be a very superficial introduction to proteins, but maybe it's useful to some of you here. So what is a protein? A protein is a polymer, and more precisely, it's a heteropolymer. That means the monomers are different, and the monomers are actually amino acids. So there are essentially 20 possible amino acids in nature. These amino acids here are represented here. This is a picture extracted from Wikipedia on amino acid webpage. And essentially, the identity of the amino acids is here in this side chain. So, and all the possible amino acids differ by a lot of different physical-chemical properties. In particular, their size, their mass, their charges, their polarity, or absence of polarity, which is very important to understand whether they like water or they don't like water, a property which is called hydrophobicity or hydrophilicity. They also differ by their genetic properties. They are coded by different codons, which are triplet of DNA bases. And all this alphabet of possible different amino acids, when they are combined together along a one-dimensional chain, actually fold into three-dimensional space and gives to the corresponding protein its structure and also its function. And a major problem in computational biology is to understand, given the amino acid sequence here, what will be the structure and what will be the function of a protein. Actually, this is some kind of, as all the statements that we'll do during the talk, this is not totally true. There exist a lot of proteins also which don't have actually a well-defined structure, which are called intrinsically disordered proteins. But let's say a lot of enzymatic proteins have a well-defined structure, and this is what we are considering here. So here you have an example of a very small domain, protein domains, which has a well-defined secondary structure. You can see beta sheets here, and also a well-defined tertiary structure, which is a fold in the three-dimensional space. And it will essentially interact with some peptide, some ligand, and trying to bind to it in a specific way. Okay? So essentially, how can we decipher from the sequence here the structure and the function of this protein? So you may ask related question. What happens if you do some kind of mutation, for instance? Suppose you have a mutation, you change one amino acid along the chain here, and what would be the effect of this mutation? So most mutation will have essentially no effect at all. They will be neutral mutation, but some of them will completely disrupt the structure, for instance, or they will change the function, so they can be detrimental or beneficial. And actually, the kind of plasticity of this material and proteins can be considered as some low scale, very small materials is very useful, and it's used a lot in engineering, where people essentially do directed evolution for protein design. So for instance, you have a natural protein, and this protein is fluorescent, but the intensity which is emitted is not very strong. So people essentially do a very large combinatorial screening of all possible mutation or a lot of mutation you can think of, and then select proteins which have a better fluorescence and so on. If you do that a lot of rounds, you end up with proteins with a very good function which can be useful for some purposes, applications. So the question is, how can we understand that? How can we understand, for instance, transition path from one protein to another one, and along the way, all the proteins will be functional, for instance. So there are many questions which are also of interest, not only for engineering, but also for evolutionary for the understanding of evolution. Of course, I mean, if we think in terms of evolution, as I just said, these proteins, or some examples of these proteins, existed a long time ago. So if we look at the last universal common ancestor, which existed billions of years ago, most of the proteins we have now actually already existed in this very ancestral organism. Proteins which have very basic functions like cutting DNA, copying DNA, and so on were already present. And during the course of evolution, they evolved and diverged in very different ways, depending on the organisms which carry these proteins. So here you have some kind of phylogenetic tree, some drawing of this tree. And if I now look at this similar proteins, in the sense proteins having very similar function and also very similar structure in very different organisms, so for instance animals here, or bacteria here, archaea, and so on, then in some way we can consider that the same function and the same structure has been sampled in many, many different ways by nature. So if we look at these different sequences, we have a lot of realization of, to a first approximation, the same structure and function. Okay? So the question is, essentially, we have a lot of realization of sequences corresponding to one particular function and structure. Can we understand some kind of function? Can we understand some kind of distribution over the sequence space which corresponds exactly to this particular function of sequence? And can we generate new sequences, for instance, having this particular function of structure? Can we understand the effect of mutation and so on? So just to summarize the purpose of the talk here, we have a lot of sequences corresponding to different organisms. Here you have humans, you have Drosophila, you have mice and many bacteria and whatever. And essentially, these are a few isolated points in the sequence space. And we can say that these are good sequences in the sense that they have a function. Many other sequences wouldn't be good sequences. And essentially what we would like to do is actually try to infer from this set of isolated points in this huge dimensional space. We'd like to infer some kind of function which has large values for the natural proteins here, probably a lot of very low values for many other proteins. And if we are able to do that, then we'll have a model over the sequence space which will help us understanding or predict what are the good sequences for this particular function or structure we are looking at. So we can ask a lot of questions, as I said before. We can look around one natural sequence, for instance, here, do some mutations, single point mutation, 2-point mutation, and predict whether these mutations are beneficial or detrimental. So this is, let's say, from the global landscape here, we try to say something about the local landscape around one particular natural sequence. Or maybe we will discover some other peak, large value here, and predict that some sequences which have never been realized by nature, never been sampled by nature, are actually good candidates for this particular protein function and structure. So this is basically the idea here. But you see immediately how formidable this challenge is, because the number of sequences of a given length is essentially exponential in the length. It's 20 to the length of a sequence. And we have a few, maybe thousands of sequences here. And the question is how to fit this function here.
Excuse me, what is the line connecting the points? What can you represent?
The model here,
yes.
It's a model we will infer. I will give you a precise meaning to that. And we hope that this model will actually predict it's a probability that a given sequence actually belongs to this particular family of sequences sharing the same function or structure. I will give a precise meaning to that, okay, in a while. So basically, we want to infer a model from a few sequences. So just to be a bit more precise, so let me tell you about more about the data. So the data we have come from protein databases, and they are of different types. So I'm just sketching some of them, but there are many, many different databases. So one type of databases are structural databases. So here is PDB, a protein data bank database, which essentially provides some sequences for which the structure is known. So there are many different ways of actually understanding and recognizing the structure. The most popular one is X-ray crystallography, which is essentially what people do. They build very dense crystals of the particular protein, which may actually have some problems because that may affect the structure in some cases. And then you can do crystallography and try to infer the position of the different amino acid of the different atoms in the protein from this X-ray data. And if you look at a function of a year here, you see the number of structures which are available in the database. And here in blue, you see the number of new structures which are added year per year, okay? And this is essentially a constant here. So that means the growth of this database is essentially linear over time, over the last years, approximately, okay? And yet there is about 100,000 structures which are known right now. Now, if you compare to what is going on in sequence databases, then the situation is completely different in the sense that the growth is essentially exponential over time. And this is essentially due to the fact that there are a lot of massive sequences techniques now, which are very cheap and very high throughput. So it's very easy to sequence different genomes from different organisms and put them in the databases. So you can see an exponential growth here. You see a big accident where the number of sequences was basically decreased by 50%. It turns out that a lot of sequences in these databases are essentially not garbage or not very well annotated and so on. So they are removed sometimes when people want just to have a cleaner and higher value, let's say more precise database. But I mean, there exist different databases corresponding to non-annotated or annotated sequences, so they are of different qualities. So just to give you an order of magnitude, the number of sequences which are available right now is about 10 to the 8. So this has to be compared to the 10 to the 5 structures I mentioned before. So the length of the sequences range for natural protein from a few tens to a few hundreds. It can be even a bit more than that. And they are from all possible origin, mostly bacteria, but also eukaryote, viruses, archaea, and so on. So this is the biggest database, but there are also databases which try to actually classify and order the different sequences corresponding to the different structures and functions which are known. So one of these databases is PFAM. So what PFAM does is basically it recognizes and proposes some different families. So by family, I mean something I have introduced before. This is an evolutionary family. So all the sequences in one family are supposed to come from a common ancestor, and they have diverged over evolutionary time. So this is how people do that. They basically try to look at the different sequences, recognize some similarity between the sequences, put them in the same family. So there are some algorithms to do that, which are based on hidden Markov models, which I will not develop. But the fact is now, if you look at the PFAM website, you can enter some name of some protein, and you will get essentially all the information you need. In the sense, you get maybe the three-dimensional structure, if it's known, for this particular family. So here is an example, which is beta-lactamase. So beta-lactamase is an interesting protein, which is generated by bacteria and which is responsible for antibiotic resistance. Okay, so it has been studied a lot. I will show you some data a little bit later. And so if you do beta-lactamase, this is this particular family here, you would see that there are about 18,000 sequences which are available, all coming from different bacteria. And there are some structures, some domains of this protein are known in structural way. And all these data come from about 3,500 organisms. So at the end of the game, what you obtain is a multi-sequence alignment. So here on the left column, you get all the sequence identities coming from the different organisms, and you get the corresponding sequences. So these sequences are aligned in the sense that they share the same format, but of course, they don't have the same length. Because during the evolution, some parts of the protein may have been deleted, other parts have been inserted along the phylogenetic tree. But here, they are just formatted all in the same way. And in order to make them have all the same lengths, you see there are some gaps here, which allows everybody to align these sequences. So when you look at this data here, there are obvious observations you can do. So for instance, look at this column here. You see that this column always carries the same amino acid. So in fact, there are a lot of sites with very conserved amino acids, so they are very conserved positions. And there might be many reasons for that. Maybe, for instance, some sites in the core of a protein are very difficult to mutate or to change. There may be also functional sites. If you change this amino acid, the specificity of a protein would change considerably. It would lose its particular function. So mutations are essentially forbidden or very rare on these positions. But there are many other positions, if I look, for instance, at this one here, where a lot of different amino acids are possible or can be found. Yes?
In order to construct these alignments, you have to insert voids.
Yes, these gaps. Yeah.
Yes. Now, this is a big combinatorial problem. how is this done?
Okay, so I didn't want to say too much about that. So people use hidden Markov models where basically, okay, so I should go into a lot of discussion about pairwise sequence alignment and so on. But essentially the idea is that if you have one sequence which serves as a template and you have another one you would like to align to it, so you try to find similarities. For instance, a portion of sequence will match another one here, and then you have, for instance, another portion of the second sequence which would match somewhere else. So you would like to put some gaps. So each time you insert a gap, for instance, then you will have to pay a cost for that. And there will be another cost if you want to stretch this gap, I mean, make it longer and longer. So essentially, there are some costs for not aligning, a penalty for not aligning. So you have, on the same site, you have two different amino acids in the two sequences. If you put a gap and so on. And the algorithm gives you something, an outcome. So this is nice, but it's not guaranteed to be the right alignment. So there are some better alignment techniques which are based on structure, which are complicated. So there is a whole, set of different techniques. And most of the time, when people are very precise, they do this kind, they apply this kind of HMM in order to do the alignment, but then they check manually. So because they know a lot about the protein, and they try to modify the alignment and make it better. So in fact, P-Farm, for instance, has a lot of protein, but there is a seed which is used to build this HMM, and this seed usually is annotated manually, and people just check that the alignment is correct on a few hundreds of sequences. Okay? So it's a science and an art. Okay, so we see So we see these positions where maybe mutations are neutral in the sense that any kind of amino acid or so can be found there. So maybe these sites are actually no interest. They don't affect at all the functional structure. This is quite possible. You may have very flexible loops in proteins. But actually, we should be careful. What may happen is that mutations are possible, but they may be correlated to other mutations on other sites. And this is something that you can understand, and this is an idea which was proposed at least 20 years ago, that if you have a primary sequence here of protein which falls in three-dimensional space, some amino acids which are very far away along the backbone of protein, but which are very close in space, may actually be strongly correlated. One mutation in one amino acid should be compensated by another one. So this is easy to realize. Suppose you have, for instance, a contact here, so two amino acids which are very close to each other. One is positively charged, the other one is negatively charged. So that's good because that basically attracts the two amino acids close to each other. If for some reason a mutation appears that the positively charged amino acid is substituted by a negative charge, then you would expect a compensatory mutation to maintain the structure and the contact, and the negatively charged amino acid should be turned into a positive one. Okay? So this will create a basic mechanism for correlation between columns in this multi-sequence alignment. And the first question which was asked, as I said, about 20 years ago, is are sequence correlation indicative for residue contacts? But of course, there could be other sources for correlations. And another one are functional constraints. You may imagine, for instance, that some ligand, some other proteins, another peptide, whatever, is going to bind some part of a protein. And there might be different kind of ligands binding here. And these different kind of ligands will create some correlation between the amino acids in order to accommodate these particular ligands. And you can think also that some sequence correlation will be indicative on this functional constraint, not about structural constraint. Okay, so how do people study these kind of constraints? How do they infer some model? And this is back to the question, to the plot, the green curve I was showing before. So the first thing to do, and actually we can discuss this, is to try to capture this correlation. And the lowest order you can go in order to capture this correlation is to look at pairwise correlation. So suppose you have your multi-sequence alignment here. You can define one particular column, I, another one, j. You can compute 1-point statistical quantities, which are the frequencies of the different amino acids along this column, which I call fi of a in the column I, fj of b in column j. And you can compute also correlation, which is the joint probability of having a and b in column I and j. Okay? So if the two columns were totally independent from each other, the two sides were independent, the connected correlation, which is just the 2-point minus the product of the 1-point frequencies, would be 0. Okay? But in fact, some pairs of sites, I and j, carries correlation which are big, and a simple estimator of a correlation is, for instance, the Frobenius norm of this matrix. So given I and j, we have a 20 by 20 matrix. We can compute the square of the elements, for instance. There are also other estimators based on mutual information, but essentially this one is very simple. And we can think that maybe if the score Fij is very big, that means that you have a lot of correlation between these two sides. That could be indicative of a contact. And in fact, it doesn't work so well. And this is the idea which was proposed a long time ago. And this is a picture which was given to me by Martin some time ago. And so here you see for a very small protein, which is trypsin inhibitor. So trypsin inhibitor is a protein which inhibits trypsin. Trypsin cleaves peptides. It's very useful for digestion. And so it contains only 53 residues in the alignment. And here you see you get bonds, which are not physical bonds. They are just links in order to show which residues are which pairs of residues correspond to large scores here, Fij. So basically, you rank, given all the pair ij, you compute these scores here, and you rank from the top Fij to the bottom one, the lowest one. You pick up maybe the top 30 scores here, and see what kind of residue they connect on the structure here. So if this is a good estimate of contacts, you should find very large Fij for pairs of residues I and j which are close to each other on the structure. Otherwise, you get some random bonds, okay? And you see that some of them, the red ones, are actually close to each other in the sense that they are distance smaller than 8 angstrom, which is a not very conservative, actually, definition of contact. But anyway, it's some definition. But many other ones, the green ones, are actually very far away, which means there are a lot of pairs ij for which this score here is large, but these sites are not in contact. So it could be, this false positive could come from other sources of correlation. They could just tell us that there are maybe some functional, historical, whatever reason for this correlation. Or maybe it comes from the fact that you may have correlations between two sites which are mediated by other amino acids. This is a well-known fact in physics. You may have strongly correlated variables which are not interacting directly, but they are interacting through another variable, okay? So we should be able to distinguish large correlation from large effective interaction. And so before I go to that, I would like to mention another approach which was based only on the correlation, which was a more sophisticated approach than looking only at correlation elements in the correlation matrix, but which was based on dimensional reduction and clustering. So this approach was introduced by Ranganathan and collaborators some time ago. And the idea there was basically look at this big correlation matrix, thisCijab, and try to look at these top components. So what you can do is plot the, for instance, the spectrum. Here, that's for the trypsin inhibitor. But if you do that for another protein, you get basically the same kind of shape. You see a few eigenvalues that are very large. And so with some criterion, for instance, above the Marchenko-Pastur edge or something like that, you can say, OK, I believe these eigenmodes correspond to some signal. So let's project all the amino acid we have in this low dimensional space. We do some kinds of dimensional reduction, which is PCA, this is principal component analysis. Do some clustering, and maybe we can isolate some clusters of sites which are, let's say, very strongly correlated. And this approach, in principle, is very nice. It's a very nice idea. So one example is given here for the PDZ domain, protein domains. So PDZ is a small protein domain which is actually used for signaling or used for binding and recognizing other proteins. So essentially, the idea is that you have a main protein here which would like to be able to recognize, which needs to be able to recognize some other proteins, and maybe, for instance, the C terminal here of these other proteins. So the first protein here will have as a subunit this domain, which is able specifically to bind to the particular sequence here at the end of this protein. Okay? So when this protein will get close to this one, it will bind, and it will signal through some allosteric change here of conformation to the main protein that the binding has occurred. Okay? And it will trigger the mechanisms and so on. And using this principal component analysis approach, what Ranganathan and collaborators found is some binding site here, and a chain of connected amino acids through the structure of these domains with some effector site here, which is supposed to be this allosteric site here, able to communicate here. You see that's some kind of Lego game here. This module is basically binding and then signaling to the protein that it's bound when it's done. So this is nice, and in fact the idea of trying to look for collective modes, functionally collective modes, is something which is very important, but there are some issues with the approach. There are some statistical issues. As we know, it's very difficult. We need a lot of data in order to be able to identify accurately large eigenvalues. I mean, there are this phenomenon of retarded learning, which was discovered a long time ago by Jean-Pierre and Tim Watkin, and known in the math literature under the name of BPP transition. So if you have some, for instance, correlation matrix with some eigenmodes with large eigenvalues compared to 1, so it's not exactly the identity matrix. So let me state it maybe in a more precise way. Suppose you have Gaussian variables, and you generate them from a covariance matrix, which is just the identity matrix, so they are just independent. Okay, but you have a finite number of these configurations that you generate independently of each other. You will get some spectrum of eigenvalue, which is called a Marchenko pass-through spectrum. Now, if you do the same thing, but one eigenvalue is not unity, so it's not the identity matrix, but it's larger than unity. If you have a sufficiently large number of configuration, you will see the corresponding eigenvalue pop out this Marchenko pass-through spectrum. But you need, it's really a phase transition. You need a minimal number of configurations to see that. There is no reason, so you see it's very difficult to extract this information if you don't have a sufficiently large number of configurations. So it's a first problem with sampling. The other problem is that the probabilistic framework here is not really well defined. So it's just a very ad hoc empirical approach. And the other problem also is that there is no trace here when you look at these modes of any structural information. And I motivated some of the question before as the search for structure in the proteins. In fact, in a paper with Simon and Martin, we saw that the structural information is encoded in the lower eigenvalue, not in the top eigenvalue. So that means blindly applying PCA on this data is actually very dangerous because we can lose a lot of information, interesting information. Okay, so as I said, one of the reasons for which looking at large correlation is not very, maybe not efficient enough, is that there might be large correlation which are not corresponding to large interaction. So how to clean the correlation matrix to keep the, let's say, some kind of direct correlation? So this was an approach which was introduced by Martin and collaborators about 8 years ago. And the idea is the following. So again, this is a multi-sequence alignment. But now let's try to model the probability of sequences in this multi-sequence alignment with some kind of graphical model. So here the graphical model is what people in statistical physics call the POTS model. So that's the next step compared to the independent site model. That's the simplest model you can think of if your sites are not independent anymore. So on each site we have a local field, which is some kind of position weight matrix. On each pair of sites, I and j, we have a 20 by 20 matrix which tells us how the two sites interact when the first one carries some amino acid and the second one carries another amino acid. So in order to parameterize this model, we have a huge number of parameters here. Okay, so you have 20 times the number of sites here, and essentially the square of that for the pairwise coefficient. Okay. So this class of model here, we would like to fit, and we would like to find the parameter on this data. So basically, we can actually find the couplings on the fields by maximizing the probability of the data, assuming all these sequences are independent from each other, which is obviously a strong assumption, because they all come from the same evolutionary tree. Then we want to maximize the product of these probabilities here over the parameters h and g. Okay? Another way to state that is essentially we would like to find the parameters j's and h, the couplings on the fields of the POTS model, such that all 1 point and all 2 point statistics moments computing from a model match exactly their counterparts in the data. Okay? So there are plenty of models which would reproduce exactly the same statistic, lower order statistics, the one you see from the data. But this one is actually a maximum entropy model. So this is the model with maximum entropy. So from an information theoretic point of view, this is the model where you don't use any kind of other information on top of this 1 point and 2 point data. So what happens when you do that? Well, you can use this, so you can infer this Gij, and which is a hard computational problem, and I'll come back to that in a while. and use the same kind of estimator. So for each pair I and j, you can sum up over a and b, j, j, b square, for instance, and rank the different pairs according to this estimator. And so I'm skipping some details here, but this is essentially the idea. And you see for this particular protein, it's really nice because all top 20 or 30 pairs here, I don't remember how many of them, they all correspond to contact. Remember what we had with the top correlation, that was not the case. So in fact, we see that a lot of top correlation or very high correlation are just mediated through two different big couplings, okay? But they do not correspond to a big statistical coupling. So they are removed by this approach. So this is very nice, but there are a lot of issues. First of all, when you infer a lot of parameters like that, it's not easy. So there are a lot of techniques to do that. So the technique may be exact, like Boltzmann machine learning. So Boltzmann machine learning is just simply intensive Monte Carlo. So essentially what you do is start from some guess of the parameters, run Monte Carlo, compute the 1 point and 2 point statistic from your model, compare to the one in the data. So for instance, if your correlation between site 1 and 3 and amino acid, valine and protein is too large, then decrease the corresponding coupling, okay? And do that for all parameters, rerun Monte Carlo, and so on. And this algorithm can be shown to be actually the gradient ascent of this likelihood here. That means it's guaranteed to converge. But it can be extremely slow. So this is not always easy to apply, but this can be done. There are also other algorithms which are more subtle, like, for instance, algorithms which try to bypass the computation of the partition function. You see, what is very intractable here is this partition function, which is the sum over all possible sequences of this Boltzmann weight. This cannot be computed. Usually, it's just an exponential effort in order to get this number, so you can try to bypass it and use approximate technique like neighborhood selection, pseudo-likelihood, which essentially do not need any computation of z, and which are guaranteed to be consistent if you have a large number of data, for instance, and your model is really a post-model. There can be other techniques coming from physics, like mean field approximation, which is very close to Gaussian inversion. So you essentially approximate the coupling matrix from the inverse of a correlation matrix, which would be true for Gaussian variables. So here we have discrete variables, so it's only an approximation. And also other techniques like cluster expansion, which try to find clusters of very strongly interacting variables and try to do that in a self-consistent way. So one problem with all these approaches is that the number of parameters to be inferred is huge. Okay, so you see that it grows quadratically with the length of the sequence. So you see, if the length of the sequence is just a few hundreds, you can have millions and millions of parameters to infer, which is a huge number. So what people do is they use regularization in order to decrease the number of effective parameters, or try to add some additional information, prior information in the inference procedure. And one example is L2 regularization, when you assume that the parameters are drawn from some Gaussian prior here, with appropriate values for the variances here. So I will come back to this point, which is interesting in a while. But there are other issues, more conceptual. So what is the interpretation of these couplings? It's very nice to say that big couplings correspond to contact, but what do they mean? Okay? And what do they mean in terms of physical-chemical interactions? And also, what do they mean in terms of other biological constraints, not only contact, but functional constraints? Another also conceptual question is, why do we keep all pairwise couplings? Probably many of them are not very interesting, actually, and they do not correspond to real interaction. And we forget completely about higher order couplings, like three-body couplings and so on. Obviously, putting all three-body couplings, four-body couplings, and so on, it's just intractable. There would be too many parameters. So either a way to try to do something where we keep some higher order couplings without actually increasing too much the number of parameters to be inferred. So I'll come back to that at the end of the talk. So just as an illustration, two applications of these techniques. So here you see some figure extracted from this paper 2 years ago, but there are more recent papers actually about that. So where these techniques for predicting long-range contacts, I mean, close in space but long range along the protein backbone, are actually inserted. Once you get this prediction, you can insert them in algorithms which are very good at folding protein sequences, okay, proteins. So this algorithm can do a very good job at folding locally a short sequence, but they're very bad at folding a very big protein. But if you give them additional information about the fact that these two sites are very close to each other in space at the end of the fold, then that helps them considerably. And you see, for instance, here, some prediction for new in the CASP11 competition. So it's a competition which happens regularly, where people, when they compute on the new structure of new proteins, before actually submitting the paper, or before actually publishing the paper with the new fold, they actually gives the sequences corresponding to this multi-sequence alignment are given, and people can actually do some prediction, blind prediction, and then once the paper comes out, they can compare. So it's a very good competition to understand the quality of the prediction algorithm. And you see it for these two proteins, which are very different. One comes from bacterium and another one from human. People were able to predict completely new fold, okay, with an accuracy of a few angstrom, which is the state of the art, essentially, right now. So you have to think that among the 16,000 family of proteins I mentioned before in PFAM, a large number actually have no known fold. So it's important to have very good prediction algorithm from a structural point of view. Another application I would like to mention is actually how to do some prediction on local mutational landscape. So here is again the example of beta-lactamase, the protein which is very important to provide bacteria with antibiotic resistance. So what people do is they can actually look at the what they call minimum inhibitory concentration of antibiotics. So you put your bacteria and with some antibiotics, if the concentration of antibiotics is very low, the bacteria will grow. If it's very large, it will stop growing. So the concentration of antibiotics at which growth is essentially over is some kind of measure of the fitness of the corresponding protein. If the protein is very good at providing antibiotic resistance to the bacterium, then it means that this concentration will be very large. Otherwise, it will be very low. So what people can do is measure the mutational landscape by considering all single-point mutation, for instance, in bacterium. And what you see here is for along the 300 sites of the protein. In this paper by Avejake, Olivier Tanayan, and collaborators, they look at all possible single-point mutation and change all amino acids one by one along the protein. Okay? And you have a color code here which indicates whether actually, when you do that, the minimum inhibitory concentration of antibiotics stopping the growth has increased or decreased compared to the wild type, which is the natural sequence. Okay, so you get a measure of a local landscape, and this is one way to measure local landscape. There are many other ways to measure by other measures of fitness, which are more connected to in vitro measurements. But if you compare this data with the prediction of the model, so essentially what you do is compute the change in the POTS energy, in the log likelihood if you prefer, when you do the mutation compared to what happens with the wild type here. You see that there is a correlation between the prediction and the measures, the experimental measures of fitness. This is not a perfect correlation, but still there is clearly some signal. And this is better than what independent site model can do. So this is nice, but one thing which is conceptually a problem here is that when you have a sequence, the only estimator we have is the POTS energy. That cannot characterize all the features of protein. So there is a conceptual problem here. You would think that the protein is characterized by many of its functional features, and a single number cannot encode everything. It will encode some mixture of everything, but we'd like to be able to separate all the different components which make up for the function. So that's a problem I would like to address also at the end. Okay, so let me turn now to the theoretical issues. So the first part will be related to existing methods, and actually one of the motivations we had in doing that is just a very simple observation. Then when you look at the priors that people use, these Gaussian priors here, you may naively think that, well, depending on the order of magnitude of the couplings you would expect, you can tune the value of gamma which corresponds. So for instance, if the couplings are expected to be of the order 1, then the gamma should be of the order 1, so that's the variance, the inverse of the variance. If the couplings are maximal couplings of the order of 10, you would expect maybe gamma to be equal to 1%, okay, 0.01, because that's the inverse of 10 squared. So it's a very naive expectation. But actually, empirically, it's known this expectation is completely wrong. And if you look at these two papers, one was by Eckeberg and collaborators in 2014, when they did structural prediction with the pseudo-likelihood algorithm, they found that the best value for gamma was somewhat proportional to the number of data, which is somewhat a little bit awkward, right? Because you would expect that the more data you have, the less need there is for regularization. But this is not at all what happens. You get better prediction for structure when gamma is scales as d, the number of data configuration, number of sequences. In another paper, which I mentioned just before very briefly, by the group of Debbie Marks and Chris Sander, where they do this kind of mutational landscape, local mutational landscape prediction, they found that gamma proportional to n, the length of a sequence, times q, which is the number of amino acids, 20, is actually very good. That gives the best prediction over many, many different families of proteins. So one empirical prediction is that gamma should scale as d. Another one, it should scale as n. You can remark that if you look at the real numbers, the length of a sequence is between 50 and 500. The number of data sequencing in each protein alignment is between 1,000 and 10,000. These two numbers are actually close to each other. But they are completely different from a mathematical scaling point of view. One is scaling as d, the other one is scaling as n, the length of a sequence. So that was one of the orientation. We wanted to understand this better. So, but let's try to develop the classical framework of Bayesian inference to see that. So we have so I will just remove all the fields here, but of course there are some fields just to lighten notations. So we have some sequences, and I will not consider amino acids with 1 to 20 values, but just let's say Isaac spins 0, 1, just also to lighten notation. But everything I'm saying can be also done for amino acids. So we have data, and these data are d configuration of length n. And I'm assuming that they're all drawn randomly, independently, from this distribution here, where we have pairwise coupling between the different sites. Z of sigma is the classical partition function we have in statistical mechanics. It's just the normalization of this probability here. Now I have some prior probability over the networks of couplings, which I assume to be Gaussian, with some unknown constant gamma here. And what I would like to define is the posterior probability over all networks here, which is just the product of these two things and normalized. So Z of j here is a new partition function, but it's not in the configuration space, it's in the network space. It's a much more complicated object, right? This is the definition here. Okay, so what is this posterior distribution? What does it look like? Well, you can imagine in this very high dimensional space of dimension n squared, there is some probability here, and there will be a maximum of the probability. And usually what people do, they look at this maximum, which is called maximum a posteriori inference. And the questions are how to compute J star, what is the effect of regularization, and so on. Okay? That's what is done in practice. But if we were true Bayesian people, what we should do is not that. What we should do is sample the posterior distribution. And of course, this posterior distribution will be dominated by networks, Jij, which have lower probability, but there are so many of them, they would dominate the partition function. When I'm talking about partition function, I'm talking about this one. The big one, okay? Not this one. So this one is actually this complicated object, but it should be dominated by some networks, which are somewhere here. And if we were able to do that, then this is not easy, first of all, because you will need to sample from the distribution of networks, but maybe there are some ways to do that. We can talk about it later. We could do a lot of things. We could compute observables, like network properties. For instance, I could define, given a site I, if I look at all the other side j, what is the square magnitude of a couplings incoming onto I? What is the magnitude of triangle here? I could define a lot of observables like that. But I could define also more subtle observable, like the model properties. If I sample somewhere here, I have a network, I generate data from this network, then what would be the likelihood of the data, for instance? Okay? So we ask questions about the generated data set from the networks which are inferred from the posterior distribution and sample from the posterior distribution. So one thing which is interesting, since most people do that, actually, is to see whether actually this thing we should do would change the outcome of this inference here. So one way to say it in a very simple way is, let me take a very simple case, which is a null model where I have pure noise. So there is nothing to infer, but I don't know it. I'm just giving data. It's only noise. So what will be my correlation matrix? It will be just a Wishart matrix drawn from a covariance matrix, which is identity, and I have D configuration of them. And I could define Q, which is the square amplitude of the couplings. Okay? If I have enough data, then obviously I will realize that all the couplings are equal to 0, and Q will go to 0. But if I have a finite number of data, something like that, I will have a Q different from 0. And this is just sampling noise here contributing to this estimator. Then if I look at the Bayesian sampling, what I can do is look at the best case. The best case is maybe by chance, I have a correlation matrix which I have measured from my data, and it's exactly 0, as it should be. I'm very lucky because in principle with a finite number of data that never happens, but maybe I'm extremely lucky. I find C equal to 0. Yet, since I have fluctuation in the space due to the fact I'm sampling from the posterior, there will be also some fluctuation in the couplings, and I can measure the intensities of the fluctuation through this Q-base parameter. So one question which is interesting is, can we compare these two other parameters here and see what is winning? Okay, so we'll see what, if we were really Bayesian people, we would have some induced fluctuation here. Would they be larger or not compared to the fluctuation we usually have in maximum a posteriori decoding? So let me consider first, without being too technical, how we can do this computation. So the first one, the map, is very easy. So we have the null model is deconfiguration of n independent random variables. So the data correlation matrix is a Wishart matrix, and I will use a high dimensional setting when the number of configuration and the size of the matrix both goes to infinity at the fixed ratio alpha. So I look for the network maximizing this posterior distribution here. And so one observation is, since this is only pure noise, I expect my correlation to be weak, of the order 1 over square root of the number of data. And in this high dimensional setting, this is also 1 over square root of the number of sites, of variables. So the Gij should be of the same order of magnitude. So it's natural to consider that the prior gamma should scale as n with some order 1 constant in front of it, which is small gamma. Now, how do we do a calculation? If I optimize this thing here, let me take a Gaussian model, just because it's much simpler. It's easy to recognize that the optimal metric J and C correlation matrix have common eigenbases. So the eigenvalues of J star may be computed very easily from the eigenvalues of C, which are distributed according to the Marshall-Kopasto distribution. So we can get explicit distribution equation or expression for any kind of observable. So one thing which is interesting is the observable corresponding to the log likelihood of a training set and the test set. So here, for alpha equal 4, just an example, I show you as a function of gamma, which is the intensity of prior, the log likelihood of a training set, which is used for inference, and the log likelihood of the test set. So I generate other noisy data, and I compute the log likelihood. So as usual, you would expect that when gamma is very small, you have no regularization. The training set log likelihood will be much higher than the test set. It's just overfitting. If you increase gamma, they will converge eventually, because there is nothing to infer. All the j should be 0, so it's a trivial fact. But now you can ask a more interesting question. Suppose you are somewhere here. You infer you do maximum a posteriori inference. You get your network, and you generate data from your network. What would be the typical log likelihood of this data? So if you do that, you find a curve in between here, which is at low gamma very close to the test set, to the training set, and at large gamma, it gets much, much closer to the test set. In particular, if you define some kind of halfway gamma at which the distance here is the same as here, you see that the generated set here is actually doing much better than the training set. And this gamma here you need in order to have that is of the order of alpha. So if you want to remove overfitting, it's the definition of overfitting, you need a very strong regularization, which is counterintuitive, but this is how it works. And in fact, this is very similar to what people have found. And this coincides exactly with what Eckeberg and other people have been doing. We see that gamma should be proportional to D, not to N. Okay? So asymptotically, when alpha is large, it should be proportional to D. Actually, it works well for all estimators which are scale independent. If you look at the estimators that people use for structure prediction, also for mutational landscape prediction, they do not depend on the absolute magnitude of the couplings, but only on the relative magnitude of the different couplings from pair to pair. So this is why having a strong generalization works well here. Okay, so let me go to the second part. So we understand map. So what happens now if I do the other things, which is more complicated? So now I'm not considering the top part of the curve here. I'm considering here this big cloud of networks. They have lower probability, but there are so many of them that they actually dominate everything in the Bayesian sampling. So I want to estimate this partition function, which is a complicated object. So let me take the best case where actually I am very lucky, I have perfect measurements, C equals 0, and I would like to estimate this other parameter, for instance. So it turns out this can be done, and there are deep connections with random matrix theory. So, and why is it so? If you take D equals 0, so we don't have this part here. So essentially, we have no samples. So you see you have a pure Gaussian measure here. So the Gij is a Gaussian symmetric random matrix. And then if we want to estimate the partition function of this model, this is exactly what Kosterlitz-Taules did in the 76. So it's exactly the spherical spin glass model, so which is well known, has been well known for 40 years. Now, if D is not 0, but of the order of n, then the situation is more complicated. Since, of course, the Gaussian measure will be biased by the free energy here. So we are not looking at typical Gaussian matrices, but we are looking at the tail of a distribution, which correspond to abnormally very large value of minus log z, because they will dominate the total partition function, this one, the big ZG. So the big value for Z sigma will correspond to the dominant term contributing to Zj. So it's a much harder calculation, but this can be done using techniques which were introduced some years ago essentially by Satya Majumdar and David Dean for large deviation of random matrices. And just as an example, this is what you get, for instance, again for alpha equals 4 as a function of gamma. Here as green, you get the Q map, which is the intensity of fluctuation of connection coming from the quench disorder in the data, which decreases as gamma increases. And this is normal because as gamma increases, you have more and more regularization. All the coupling goes to 0, so Q should go to 0. If you do the same thing and you have perfect measurements, but you take into account Bayesian fluctuation, you get something like that, which is bigger. And in particular, it's bigger above some gamma, which is smaller than gamma 0 I mentioned before. So the conclusion of this thing is that in the regime where people use MAP routinely for proteins, if we were able to use to do Bayesian inference, we would have fluctuations which are bigger than the one we have in MAP. So that means Bayesian fluctuation would be relevant. So they could change considerably the quality of a prediction. So would it increase the performance of prediction or not? Probably yes, but we don't know. And that's an open question which I think is interesting. Another thing I think which has not been recognized enough, but maybe I'm wrong in the statistical inference community, is the importance of entropy. Usually people look very much at the top, they maximize this thing and do a lot of efforts to get close to the maximum and so on. But in fact, there is such a huge entropy that if you do Bayesian inference, you will be stuck somewhere much lower value. I'm not aware of many studies about this entropic effect, and I think maybe statistical physics could be useful to recognize the importance and characterize the effect of these entropic terms here. So maybe I will go very quickly on the second part. I wanted to go also to the other part, the last part, which is extension. How can we go beyond the post-Mollen and pairwise couplings? So I would like to mention some work on ongoing work on restricted Boltzmann machine. So that's the kind of model which comes from machine learning. Actually, it was invented a long time ago, about 30 years ago. So restricted Boltzmann machines are extension of Boltzmann machines, and they may be defined formally as follows. So you have machines with two layers of units. One layer is called visible layer. So for simplicity, I will assume here that there are binary units. But in fact, in the application to protein, there should be amino acid units in the sense that they should take 20 different values. And you have some hidden layer where you have some real variables. And these are simple Boltzmann machines in the sense that you have a Boltzmann distribution for the joint distribution of the visible configuration and the hidden configuration, where the graph of connection is bipartite. That means you have connection between the visible units and the hidden units here, but there is no connection within the hidden layer and no connection within the visible layer. So there will be some kind of local potential acting on each visible unit, a potential acting on each hidden unit. Since there are real variables, it could be any potential u. And this defines completely the joint distribution. So the idea of a restricted Boltzmann machine is that we would like to fit the marginal distribution over the visible configuration to the data. So essentially, it's let's say, a complementary point of view with respect to Boltzmann machine. When you have configuration of variables and you observe a correlation between the variables, one way to model this correlation is to put interaction. And this is what we would do usually in physics, and this is exactly what was done before in the approach I mentioned. You put effective interactions, and you expect that this effective interaction will reproduce the correlation you see in the data. Another way, which is very common, for instance, in neuroscience, is to say, OK, I see correlations. They may be due to common inputs. There is no direct interaction between the units, but there might be other inputs coming from other units which drive my two units together, and they will be effectively correlated. And this is the idea behind a recessive Boltzmann machine. So this will be the layer of common inputs, which will produce some correlation between these visible units here. So essentially what we have to do is to integrate, formally what we have to do is to integrate over all visible, all hidden unit configuration here that defines the marginal distribution over the visible configuration. And this thing should be fitted to the data. So that means we provide a lot of data to that and maximize the product over all the data of this P of V. Okay? So this is a tough problem, but over the last 10 years, a lot of progress has been done in order to do that in practice, especially with the contrastive divergence algorithm by Hinton and collaborators, and also subsequent algorithms. So what happens if you do that? One thing I would like to mention first is that this is a direct extension of the usual Ising and Potts model we have in statistical mechanics. So why? Suppose that U of H, this potential here, is a quadratic potential. So here is a calculation, which is actually a trivial calculation. If you put U of H here equal to a quadratic things, it's very easy to compute the marginal distribution. This is just a Gaussian integral over the hidden variables. And you will get an effective energy over the visible layer, which correspond to the local potential we had, and also some effective couplings corresponding to this Gaussian integration. So you see that here we get an effective matrix of couplings, which is just the sum over all different hidden units of a Wi mu W J mu, which are the couplings coming to the same hidden unit mu from two visible units I and j, and you sum over all mu's. So essentially, if we choose U of H equal to H squared, the quadratic thing, the machine we are considering is nothing but the machine we consider usually in statistical mechanics. But there is no reason to choose this. Actually, there are good reasons not to choose that, and people in machine learning have been knowing that for a long time, but maybe in statistical physics we have been much, much slower at recognizing this. If we use non-quadratic potential, and there are many different ways of choosing the potential, so one way that people use is rectify linear units, and that corresponds to a potential which instead of being quadratic is quadratic only at large values here, but may have some linear slope here and maybe some hard wall to prevent from negative values of H. These kind of potentials are much better, in sense practically when you empirically. So, and what people observe, and this is a picture extracted from this paper, where they train a recessive Boltzmann machine on MNIST, which is a famous data set of handwritten digits. They observe that the kind of weights of representation that this RBM have depends very much on the structural parameters, so how many hidden units you have. So here is the machine, so this MNIST data, there, yes?
So the matrix is not general, the J matrix that you obtain is a projector, sum of projector.
Yes, I agree, yes.
Well, no, you don't know if your J matrix, is it like this?
Yes, it's a, yes, you mean that all the eigenvalues should be positive?
No, I was saying that you're not reconstructing the most general Ising model.
Well, apart from this point, this problem.
On the number of mu that
yes, but if you have a larger number of hidden units, then you can construct a lot of things. Okay, so just to give you an idea, so the images of MNIST digits, they are 28 by 28 pixels, and each hidden unit is seeing these 28 by 28 images of, let's say, white and black pixels. And so you put an image in the visible layer, which is this thing here. You will activate the different hidden units. And then in turn, once you get this configuration of activation of hidden units, you sample back on the visible layer some pixels, right? And do that back and forth. Every step is very easy because all conditioned to one layer, all the units in the other layers are independent. So it's very easy to sample. That was one of the reasons why people were very interested in these machines. So now you do that. You do training, and you look at the kind of features which are inferred at the end of the training. And you see if the number of hidden units is small, I hope you can see something here. So here you see the weights, so 28 by 28 for each one of the 16 hidden units in the hidden layer. You see the different weights which are connected to these particular hidden units. Is it clear what is shown here? Okay, so you have this image. So you have your input layer here. This is MNIST. So you have this 28 by 28 pixel. So it's 28 by 28. And not 4 by 4, but OK. And then each hidden unit here has connection with each one of the pixels. So if I look at this connection here, OK, from above, this is what I see for each one of these 16 units. So what you see here is that they look very much prototypes of digits. You can recognize the different digits, OK? And while if you do with 100 hidden units, then you see small patches here, small dots. So the color black or white means they correspond to negative or positive weights, and they have nothing to do with digits, OK? So if you look at now in terms of statistical physics more precisely what this different regime means, in fact, there is clearly a phase transition in between these two regimes. So the first regime is very similar to the Hopfield model regime that has been known for a long time in statistical mechanics. And that corresponds to when you if you look at the likely configuration, high probability configuration in this visible layer, they will essentially activate one hidden unit very strongly. And this is the retrieval regime of the Hopfield model, the ferromagnetic phase in statistical physics language. All the other hidden units, they will do nothing. They will be weakly activated. So here's the beauty of this potential compared to what people do usually in the Hopfield model. In the Hopfield model, you have a quadratic potential. So the hidden units can have the ones which are not strongly activated can have noisy values, small ones. They will add up. At some point, you get too many of them. And this is the critical capacity of the Hopfield model. So that limits the size of the top layer to this 0.14 that people computed a long time ago, times the number of visible units. But if you have potential like that, since the beginning at small h has a L1 regularization, it's a linear potential, it's not a quadratic potential, then it's very hard for h to take values different from 0, especially when the slope is very large, because it would cost too much in energy. So that means a lot of these hidden units will be silenced, so you can have many of them. They will be set to 0. They won't interfere with these hidden units here. So if I am one of the visible units, I will receive a lot of very strong input from this one, essentially a lot of zeros from these ones. I'm very happy, and I will stabilize in one of these prototypes. And this is much better than the Hopfield model because it kills noise. Now, the other regime is actually interesting, and we have spent some time with Jérôme about trying to understand this. So now you see these kind of features, and the question is how do you combine them in order to make some digit? In fact, what happens is a different regime where you have a large number, large compared to 1, but small compared to the total number of hidden units, which are strongly activated. And they all, let's say, combine together in order to, when you add all these small patches on the visible layer, to form a well-defined digit. So it's a much more efficient way of coding for configuration, which is combinatorial. And so there are very nice sampling properties. These machines are much more efficient in terms of sampling compared to the Hopfield model. Activated processes are much faster. So one question we ask is whether we can see that also in protein data, and I will be very brief. We'll show you some results we have for lattice protein data. So they are not real data, they are just synthetic data. So just to give you a glimpse at the lattice protein world. So lattice protein were invented a long time ago. This is just one model from Gutin and Sachnovich in 1990. And I like them very much because they are totally under control, and we can see what we do with this machine. So the numbers. So there are proteins which are expressed on a very small cube, 3 by 3 by 3. So that means you have 27 sites. So the number of sequences you can think of, you can have is 20 to the 27, which is 10 to the 35. Now, what is a protein fold? It's a way you can arrange a polymer of 27 sites on this 3 by 3 by 3 cube. You see 4 different folds here. Can you see them? Yes? There are 104,306 ways of doing that, which was enumerated by Sachnovich. So 10 to the 5. Each one will define a structural family. And we can essentially, so if you look at all the set of all sequences, we can define the sequences which fall in one of these particular structure with probability larger than 0.99. That means the energy in this fold is much smaller for this particular sequence compared to the other one. That defines a subset here. The number of sequences in each fold, like that, is about of 10 to the 22, 10 to the 25, depending on the fold. So if you multiply this by this, you see you get a number which is much smaller than that. I mean, most of the sequences actually don't fall in anything. So it looks like a little bit real sequences, real proteins. So what we can do is take one of these structure here, generate a multi-sequence alignment, and give it to the RBM, and the RBM will give us something. So here's the structure, which is in competition with 100 other thousandfold. So if the number of hidden units is sufficient, we see this kind of compositional phase, where the features become really localized on a few sites. So here is, for instance, one feature. So we have 100 hidden units. I will show only 3 of them. So for instance, here, so we have a sequence logo. So along X, you see the site. And along Y, you see the intensity of a coupling corresponding to this particular hidden units, which can be either positive or negative. And we represent the corresponding letter with the size proportional to the intensity of a coupling. Is it OK? So it's just sequence logo representation. So you see, this hidden unit, particular hidden unit, is looking at 2 different sites and is trying to impose some particular configuration. So, and it will be active if you have, for instance, amino acid G and G on one side, cysteine or cysteine, for instance, here you have C and C, and will be, for instance, deactivated if you get, for instance, positive charges and negative charges amino acid on the 2 sides. And these kind of features correspond to contacts. So you see highly localized features on contacts, and this is similar to one thing we did with Simona and Martin some years ago when we look at the eigenmodes of the correlation matrix. But you see other features which are actually not localized on 2 sites, but are localized on triplets. So for instance, amino acid 12 and 14, they have some weights, and they all project onto 19. They're all in contact with 19, which has larger weights. So that tells you that how to maintain the structure here is you have to maintain the 2 contacts, and they are not independent constraints because they both touch the same amino acid. And this is something you can see clearly here in this feature. So you can see other features which are more extended. And this one is interesting. That's a kind of electrostatic extended mode, where if you look at this particular amino acid here, in order to realize the contact in this subset, you can choose plus, minus amino acids, or just the other way. Okay? And in fact, if you look at the distribution of sequences, there are really 2 different peaks corresponding to these 2 different realizations. So these are 2 different modes in the data distribution. And you can sample conditioning to one particular hidden unit and look at the distribution that you get, and you still get very very good sequences, but which realize only one of the 2 configurations. So in fact, so we hope that this kind of approach, which goes one step beyond the POTS model, will be able actually to disentangle all the different contributions to the function of proteins, and will be able to make some design in the sense that you can basically condition on the hidden layer here, modify the activity in the hidden layer, and generate some particular proteins with some particular features. So that's the hope. And this is what we are doing now on real data. OK, so I think I will stop here because I'm well beyond that.
Thank you for a very nice talk. My question is about the likelihood. You mentioned at some point that in one slide, the likelihood was a product of the likelihood of the individual proteins, and you mentioned that it's a hard assumption, particularly because of evolution, right? Yes, so I suspect that the structure of evolution creates confounding factors in all these things. Yes. So could you be more precise on how it's dealt with? Like, is it ignored or in practice in the publications?
I would like to say it's taken into account, but I should say it's essentially ignored in the sense that so you have different problems. You have the problem of evolutionary constraints, and you have the problem that biology lab are more interesting in some organisms than other organisms. Okay, which actually is a problem which may be actually currently solved because people can do, with metagenomics, they can do a lot of things which are basically random. But so what you can do, and what was done some time ago, is essentially see that when you have in the sequence space a sequence which is surrounded by many similar sequences, you can try to give a low weight to this thing here, because compared to other ones, so some kind of uniformization along sequences. But that's a bad answer, right? Good answer should be, so you should try to take into account this phylogenetic, this evolutionary process. But then the problem when you do that is that you have to make some assumption about the models for evolution. So it's a big industry. reliable are the models, it's not something obvious. So, so I don't know. I mean, but it's an important question, I agree.
Yes, when you feed the POTS model on the data, could be something be noticed on the typical range of interaction? I mean, the order of the length, or is it completely spread over all possible lengths?
You mean
for high correlations?
If I look at the Jij, which are inferred,
Yes.
and I look at how far away are I
Right.
and J on the backbone,
Yes.
yes, I mean, you can find anything. You know, they can be very close to each other in space and very far away along the backbone.
And there is no upper bound on the length of interactions that can be observed in practice? Or?
Okay, so you can see, I mean, strong interaction which corresponds to secondary motifs. So you can and also strong interaction for amino acids which are close to each other along the backbone.
Right.
So that you see. So you see some locality. But I mean, maybe the most interesting contacts or couplings are the ones which are far away because these kind of effects are well known. Okay.
We had maybe a long seminar already. So let's thank our speaker again.